Hi students. Today we are going to learn one of the important topics from the complex number is geometry of complex numbers. Okay, the geometry of complex numbers. From this concept we will get the questions in IIT JEE mains and advanced. Okay, it is an important topic. So we have to solve more problems based on this concept. Okay, so the geometry of complex numbers. So whatever we learned in the previous classes are in this present plus 2 standard, what it is, straight lines, pair of straight lines, and section formulas were related to the straight lines and perpendicular distance from a point to a straight line, and equation of a circle, equation of an ellipse, and everything can be represented with the help of the geometry applications are represented with the help of the complex numbers. Okay, so that's why we this is an important topic to us for the competitive examination. Now we'll discuss one by one how to represent the different types of locus in Argand plane. Okay, that means this is also be, we can term it as different types of locus in Argand plane, locus of the complex number in Argand plane. For example, I am considering the first thing I am considering as a distance formula. Okay, distance formula. So what it is, let in general we represent it as a, let A is a point and B is another point. A and B are the points. Then the distance between the 2 points, if the points are x1 y1 and x2 y2, now the A must be represented with a complex number z1 and B is represented with complex number z2. So the distance between the 2 points A B, okay, A B, so which can be written as simply nothing but modulus of z2 minus z1. Okay, AB modulus, that means AB length is equals to the modulus of the complex numbers difference between the z2 and z1. So let z1 equals to x1 plus I1 iy1 and z2 equals to x2 plus I times of y2. Then what it is, if z2 minus z1, what will get, z2 minus z1 means separate the real parts as a, that means x2 minus x1 as a real part and y2 minus y1 as imaginary part. Then the modulus of this one z2 minus z1 is equals to square root of x2 minus x1 whole square plus y2 minus y1 whole square. So now, which is nothing but the square root of x2 minus x1 whole square plus y2 minus y1 is nothing but the distance between the 2 points. Okay, the distance between any 2 points in Cartesian plane. Okay, distance between 2 points. Okay, so in Argand plane, the 2 points are represented with, one is a complex number z1 and another one is a complex number z2. Then the distance between the two complex numbers is nothing but represented by mod of z2 minus z1. Okay. So next we're moving the next formula, that is the perpendicular bisector. Okay, the next one is perpendicular bisector. So perpendicular bisector, let we are considering A is a point and B is another point. So A is a complex number z1 and B is represented with a complex number z2. Then we are considering what is a point P, which is a complex number z. Now the perpendicular bisector, so now it is dividing the AB line segment, joining the line segment AB, that means joining the line Z1 and Z2 is perpendicularly bisected by the point P with the complex number Z1. Now in this case what should be considered? So in this case, so whenever it is perpendicular bisecting means the distance of from point A to P and point B to P must be equal. So for a perpendicular bisector, PA must be equals to PB. Okay, so if we consider PA, that means in the vector form we can write as OA minus OP. The modulus PA is the length now. Okay, PA is the distance between, that means it is a length. So then we can write as OA minus OP. So APR we can write as what it is, Z minus Z1 or Z1 minus Z2. Magnitude is the same. So we can write as Z minus Z1 equals to Z2 sorry Z minus Z2. Okay, Z minus Z1 equals to Z minus Z2. So, and if we consider at any point, if P is taken, the complex number Z is taken over here. So, wherever we can take the AP and distance between the BP. If it is a perpendicular bisector, then the distance between the 2 points AP and BP always must be equal. AP and BP must be equal. Now this point, okay, the point Z is, so if we take in this line, okay, wherever we consider the point Z, it must be the having the same length. Now the what is the locus of Z? The locus of Z, okay, the locus of Z, we can say it is as locus of the complex number Z is a, okay, what it is, a perpendicular bisector. Okay, is a perpendicular bisector. Okay, is a perpendicular bisector of line joining Z1 and Z2, lining Z1 and Z2. Okay, which is the formula of a perpendicular bisector. Now what is the formula for perpendicular bisector? Z1 minus Z or Z minus Z1 mod less equals to mod of Z2 minus Z or Z minus Z2, which is if a complex number is given in this form, that means the Z is a perpendicular bisector. Okay, Z minus Z1 equals to mod of Z minus Z2. Okay, next moving further, next formula, section formula. Okay, section formula. So we line joining Z1 and Z2, line joining Z1 and Z2, that means it is a point Z1 and point Z2, that means represented with a point A and represented with a point B and a point P. Okay, a point P is dividing this line segment AB. Okay, point P is dividing the line segment AP. Okay, in m is to n ratio, in m is to n ratio. Then we can say that now what is the locus of Z, which is nothing but the Z is internally dividing the line joining A and B in m is to n ratio. Then we can write it as Z equals to, okay, Z equals to m times of Z2 plus n times of Z1 by m plus n. Okay, by m plus n. Okay, so which is the section formula, and we can represent this is as a the locus of Z. Okay, which is nothing but which is also be written as locus of Z. Okay, the locus of Z. Okay, Z is over here. Now you can move the Z towards left or you can move towards the B side. Okay, towards the A side or towards the B side. For example, I am considering so A and B, that means Z1 and Z2. Now the point P is over here. Okay, the point P is moving. Okay, the point P is moving in between Z1 and Z2. That means in between the points A and B, the point Z is moving. Okay, the point Z is moving in between A and B. Now what is the movement? That means the locus of Z joining the line segments, joining the line segments Z1 and Z2. Okay, joining the line segment Z1 and Z2. Now how to find out this? We know that Z, wherever it is the Z either in this place or in this place. Now the distance between point A to point P and point P to point B, if we add this distance, so that means this is, let's consider some distance as x1 and BP as some x2. So x1 plus x2 has to be give the result as AB. So we can write it as AP plus what it is BP, the distance between these two. If we add these two, x1 plus x2, that means AP plus BP, the distance has to be give as total the line segment. What it is, total line segment is AB. Okay, the total line segment is AB. So now if we represent in AP is the length, in complex numbers that is represented as Z minus Z1 mod plus and BP Z minus Z2 mod equals to mod of Z1 minus Z2 or Z2 minus Z1. Okay, mod of Z2 minus Z1 or Z1 minus Z2. So modulus is a quantity and you can find it as any way. The resultant is same, either Z1 minus Z2 mod or Z2 minus Z1, the modulus is same. Okay, so we can write this is as Z2 minus Z1. So if it is Z minus mod of Z minus Z1 plus mod of Z minus Z2 equals to mod of Z2 minus Z1, then that is represents, now which represents the locus of Z joining the line segments Z1 and Z2. Okay, so the Z in between the A and B, the Z has to lie in between the A and B. It always moves on the line joining the line segment A and B. So now we consider the next fourth one. So what it is, we are having a point A over here which represents the complex number Z1 and a point B which represents the complex number Z2 and which is moving in this way. Let here the point P represents. Okay, here the point P represents. So now we can write this as, so total to find the A B. Okay, total find the length of AP and if we subtract from this one the length of BP. Okay, if we subtract the length of BP, then we can find the length of AB. So I can write this is as what it is, AP. Okay, AP minus BP equals to, we will get it as AB. Okay, so now AP, so AP means OP minus OA, that means Z minus Z1 modulus equal, sorry, minus Z minus Z1 modulus minus mod of BP can be written as Z minus Z2 equals to mod of Z2 minus Z1. So before the case, what we obtained, mod of Z minus Z1 plus mod of Z minus Z2 equals to mod Z2 minus Z1. Okay, mod of Z2 minus Z1. So if it is placed, the point locus of Z, it only lies in between the A and B. Now the locus of Z is outside A and B. Okay, outside the point B, but it is initiated with point A. So now we can say that which is the formula. This is the formula for locus of Z. Okay, which is the formula for locus of Z. Okay, locus of Z, and Z is a ray. Okay, Z is a ray. Okay, Z is a ray initiating from Z1. Okay, initiating from Z1. Okay, if which is in the form Z minus Z1 mod of Z minus Z1 minus mod of Z minus Z2 equals to mod Z2 minus Z1 is nothing but locus of the point Z, and Z is a ray which is initiated from a point, that means which is initiated from the complex number Z1. Now if which is moving, okay, if A is a point and B is another point. Now if this P is towards the left side, now P is towards the left side. Okay, just before we discussed here, the P is right side. Now if the P is towards the left side, that means the P is moving either towards the left side or towards the right side. Okay, towards the left side or towards the right side, but it is not lying in between A and B. Okay, it is not lying in between A and B. Okay, then we'll obtain the same thing. What it is, if it is towards the left side or if it is towards the right side. For example, if it is over here, to obtain the distance AB, so if it is right side, so AB, to obtain the distance AB, first we need to find out the BP and we need to subtract the, okay, then we need to subtract the AP. Okay, so that means it is same as the above. Okay, so for this one, just simply, which is the same formula, Z minus Z1 minus mod of Z minus Z2, but we need to consider the whole modulus. So if we consider the modulus, either it will move towards the left of the line segment AB or it will move towards the right of the line segment AB, then we will get the required formula. So which is nothing but the straight line. Okay, straight line. Okay, we can say this as straight line locus of Z. Okay, locus of Z, where the point Z does not lie between, point Z does not lie between A and B, does not lie between A and B. That means complex number Z1 and between complex number Z2. Okay, between the complex number Z1 and complex number Z2. I think you understand this, how the line segment can be represented with the complex numbers, how the line segment can be represented with the complex numbers. And moving forward, next we will discuss circle, how to represent a circle using the complex number. Next one is the fifth one, equation of a circle. Equation of circle. And we know that, so in an Argand plane, let we are having an Argand plane. Okay, in an Argand plane, let which is a circle. Okay, where which is the center, which is represented by Z1. Now which is the point on the circle, let I am representing with Z. Now the locus of Z. Okay, now the Z is moving. Okay, the locus of Z, we need to find the locus of Z. To find the locus of Z, first we need to find the distance between C and P. Let I am considering the distance between C and P as R. So now we can write this as, so what it is, CP. Okay, the length means magnitude equals to R. Okay, where in the vector form we can write this as CP as position vector OP minus OC. So we can write it as OP minus OC as, so position vectors means in terms of vector we can write it as what it is, Z minus Z1, mod of Z minus Z1 equals to R. Okay, which represents the equation of a circle in complex numbers having the center as Z1. Okay, having the center as Z1 and the radius as R. Okay, for example, if the Z1 equals to 3 plus 4i, if the Z1 equals to 3 plus 4i, that means now what it is, the center of this circle is, center of this circle is what it is, 3 comma 4 and the radius is 5. Okay, radius is 5, distance between the, what it is, we obtain CP equals to 5, radius from the point P. Okay, so now we can find out, okay, not is the radius, radius is not 5, we can find, we have to find the radius with the given condition of Z. Okay, so if it is in the form of Z minus Z1 and mod of Z minus Z1 equals to R is the equation of a circle in complex number. So if the circle is, okay, if the circle is having the center as origin, okay, if the circle is having the center as origin, now which is point P of Z, which is the Z1 is the, what is, origin. Now P is moving the locus of P, that means the locus of Z is nothing but, so OP, distance from the origin equals to R. Okay, the distance from the origin equals to r. Then we can write as z minus origin. Origin is 0 only here. Okay, the center is 0 0. Then we can write as mod z is equals to r represents us. Okay, mod z is equals to r represents us the equation of a circle having the center as origin. Okay, the equation of a circle having the center as origin, whereas mod of z minus z1 equals to or represents the equation of a circle having the center as z1. Okay, so we can also represent the circle in a different form, that is as a diametric form. Okay, the circle as a diametric form. So what is the diametric form we must have in a circle? We must consider a diametric a and b. Okay, a and b is a diametric. That means if we consider a and b at any point on the circle, at any point on the circle, the semicircle, okay, the semicircle, now at any point on the circle, the semicircle angle is 90 degrees. Let I am considering p is a point over here. So the semicircle angle is p of complex number z. Now the locus we need to find in this semicircle, so which is nothing but circle equation in its diametric form. Okay, we can obtain this is as what it is. If it is a right angle, we can write it as ap square plus pb square equals to ab square. Okay, why? Because it forms a right angle triangle. Then apply the Pythagoras theorem. AB is a hypotenuse and we will get it as ap square plus pb square equals to ab square, and we can write this is as ap square as z minus z1 mod of z minus z1 whole square plus mod of z minus z2 whole square equals to mod of z1 minus z2 or z2 minus z1 whole square. Okay, which is the equation of a circle in diametric form. Okay, we learned the circle equation size z minus z1 mod of z minus z1 equals to r having the center as z1, and mod z is equals to r having the center as origin, and another form is the diametric form of a circle. Mod of z minus z1 whole square plus mod of z minus z2 whole square equals to mod of z1 minus z2 or z2 minus z1 whole square, and we can represent this in argument of z minus z1 by z minus z2. Okay, argument of z minus z1 by z minus z2 equals to plus or minus pi by 2. Okay, which represents also a diametric form of a circle. Okay, which is also represents the diametric form of a circle. Why? Because so the in the semicircle diametric form, the semicircle will forms the 180, what is 90 degrees angle, the semicircle which forms the 90 degrees angle. Okay, okay, now next we will discuss about the ellipse, how to represent the ellipse, or which is the sixth one. Okay, ellipse using the complex number. Okay, the ellipse using the complex numbers are represented by z minus z1 mod z minus z1 plus mod of z minus z2 equals to some constant k. Okay, is ellipse. Okay, which is represented as ellipse, which is represented as ellipse. What condition it has to be satisfied is if k is greater than mod of z1 minus z2. If k is greater than mod of z1 minus z2. We know that in ellipse we have the two foci points, that means focal points. One is as s dash and another one is as s. Okay, generally the s dash is represented, s is represented by ae comma 0 and s dash is represented by minus ae comma 0. Okay, and we are considering a point P over here which is represented by complex number z. Now here the s dash is represented by in terms of the complex number as z1 and s is represented by in terms of the complex number as z2. We know that in ellipse, okay, we know that in ellipse what it is, sp plus s dash p equals to 2a. Okay, sp plus s dash p equals to 2a, and we know that s dash equals to 2a E. Okay, where E is the eccentricity of ellipse. For ellipse, the eccentricity is less than 1. Okay, for ellipse, the eccentricity is less than 1. Okay, SP plus S dash P. And how to represent SP? SP is nothing but OP minus OS dash, which is nothing but the mod of Z minus Z1, and S dash P is represented as, so okay, S dash P is represented as mod of Z minus Z1, and SP is represented as mod of Z minus Z2 equals to 2A, otherwise a constant K. Okay, then I can represent this as a constant K. Okay, so where K equals to 2A, and we have 2A and 2AE. Okay, where 2A and 2AE, where it is 2AE? S dash. So now the distance between the S and S dash, which is nothing but mod of Z1 minus Z2 or Z2 minus Z1, which is equals to 2AE. And if we consider 2A and 2A is where A, what is eccentricity is less than 1. If eccentricity is less than 1, 2A is always greater than the 2AE. So that means we can write it as 2A is always greater than, so what is 2AE is nothing but S dash. So we can write as Z1 minus mod of Z1 minus Z2, and we represented this 2A as with some constant K. Now K has to be greater than mod of Z1 minus Z2, which is the locus of Z. Okay, this locus of Z, if it is in the form of mod of Z minus Z1 plus mod of Z minus Z2 equals to some constant, and if the constant is greater than the distance between the Z1 and Z2, if the constant is greater than between the distance of Z1 and Z2, then that represents us the locus of complex number Z as ellipse. Okay, the locus of Z as ellipse. Now we will discuss hyperbola. Okay, hyperbola. So what is hyperbola? In hyperbola, the condition it has to be satisfied is, so again it is Z minus Z1 mod of Z minus Z1 minus mod of Z minus Z2 whole modulus equals to K. Okay, where before that we didn't consider whole modulus. Now it is, what is hyperbola, which is hyperbola if the condition it has to be satisfied. Now the K has to be less than, what it is, mod of Z1 minus Z2. Okay, so that means what should be considered? We have again here the hyperbola. Let this is as representation for hyperbola, and here we have the focal point, that means S dash as some complex number Z1, and here we have S as some complex number Z2. Let we are considering a point P over here, P of Z, then which is SP, and which is the S dash P. So we know that in the hyperbola, the difference between the, what is the focal distances. Okay, the difference hyperbola, the difference of the focal distance is 2A. So whereas in what is SP plus S dash P equals to 2A we obtained in ellipse, but here S dash P or SP, or that means S dash P minus SP, the difference, either whatever it is, the difference between these two must be equals to the, what it is, focal distance. Hyperbola difference of focal distances is 2A, and we know that that means S dash equals to again 2A E. Okay, S dash equals to 2A, where S dash can be written as mod of Z1 minus Z2. Okay, mod of Z1 minus Z2 equals to 2A E. So where now coming to here, so S dash P minus SP equals to 2A, and we can write this is as S dash P as mod of, which is ln mod of Z minus Z1. Again we have the mod over here minus, and SP can be written as Z minus Z2 mod equals to now some constant K. Now what it is 2A and compare 2AE, where K equals to 2A, 2A and 2A, where for this hyperbola the eccentricity is greater than 1. Okay, if 2A is multiplied by greater than 1, then 2A is always less than. Then we can write as 2A is, what is K is less than 2AE, which is nothing but mod of z1 minus z2. Okay, to AE mod of z1 minus z2. So now if any given complex number equation mod z1 z minus z1 minus mod z minus z2 equals to some constant, and now check this constant whether this constant is greater than or less than. If it is less than the distance between the z1 and z2, if it is less than the distance between the z1 and z2, then we can say that the locus of the given point z is an hyperbola. Okay, I think you understand these concepts, and when in the next lecture we will analyze these concepts with the examples. Thank you very much.